On July 11th, 2017, NASA's Juno spacecraft dropped to within 1,600 miles of Jupiter's cloud tops and flew directly over a storm that humans had been staring at through telescopes for more than 2 centuries without ever knowing how deep it actually went. Scientists had spent 200 years watching the great red spot swirl on the surface with no way of confirming whether it was a thin, decorative smear of weather or something monstrous reaching down into the planet itself. When Juno's microwave radiometer finally punched through the clouds and sent its data home, the answer stunned even the researchers who had spent their careers preparing for it. The storm didn't stop at the clouds. It kept going, plunging at least 200 miles, and by some estimates as much as 300 miles, straight down into Jupiter's atmosphere, 30 to 100 times deeper than the deepest point in any ocean on Earth. A storm wider than our entire planet, with roots reaching down farther than anyone had dared to guess. And that single discovery is really just the opening chapter of something far bigger. Because if you could take a drill capable of surviving the worst conditions in the solar system and punch straight down through every planet and moon we know, what you'd find below the surface is stranger, hotter, and more violent than almost anyone realizes. Every single world you've ever looked up at in the night sky is hiding an entirely different planet inside it. One built from crushing pressure, molten metal, and heat that would vaporize almost anything humans have ever built. So let's do exactly that. Planet by planet, moon by moon, straight down to the core, starting with the object closest to home and ending somewhere far stranger than anyone expects. Start close to home on the moon. Land on its gray, sunlit surface under a jet black sky. No blue up there because there's barely enough atmosphere to scatter any light at all. Drill straight down and the first layer you hit is the crust. And on the near side, the side that always faces Earth, it runs about 43 miles thick. Flip to the far side and that same crust is more than twice as deep. The moon is a rocky body through and through, its outer shell built mostly from silicon, iron, aluminum, calcium, oxygen, and magnesium. Keep drilling and you drop into the mantle, a long and grinding hall roughly 850 miles thick, growing hotter with every mile, packed with dense minerals like pyroxene and olivine. Break through that, and you hit a semi-molten outer core, another 93 miles of scalding material, before finally reaching a liquid iron shell nearly 60 miles thick that would melt an ordinary drill bit in seconds. At the very center sits a solid iron core, roughly 150 miles thick, dense enough that punching through it would tell you almost nothing new, so plant a flag and move on. Next stop, Mercury, the smallest planet in the solar system, and, thanks to its proximity to the sun, even hotter on the surface than the deep interior of the moon. Mercury's outer shell, crust, and mantle combined runs about 250 miles deep, broadly similar in composition to Earth's own layers. Then the drill slams into something almost nothing else in the solar system can match. A solid metal core more than 2,100 miles across, consuming roughly 85% of the entire planet's diameter. For comparison, Earth's core takes up barely half of our planet's diameter. Mercury is, proportionally, almost all core with a thin, rocky shell wrapped around it like an afterthought. And there's no drilling through that. On to Mars, where the sky glows a hazy, dusty blue-orange at sunset. Mars's crust is thin compared to Earth's, somewhere between 6 and 30 miles deep, built from iron, aluminum, calcium, potassium, and magnesium, chemically close enough to Earth's own crust that it's part of the reason scientists keep circling back to Mars as humanity's most realistic off-world home. Push through into the mantle, a rocky layer roughly 100 miles thick, and you'll notice something Mars doesn't have much of anymore: activity. There's no boiling magma churning close to the surface, which is exactly why Mars has been geologically quiet for hundreds of millions of years. NASA's InSight lander, which touched down on Mars in November 2018, spent 4 years listening for Marsquakes with a seismometer and confirmed that the planet's insides really have gone largely still. Keep drilling, and you eventually strike Mars's core, an iron, nickel, and sulfur ball somewhere between 2,000 and 2,600 miles across, bigger than Mercury's core in raw size, but Mars itself is the bigger planet, so the proportions still make sense. Interestingly, InSight's seismic data also revealed that Mars's core is entirely liquid, unlike Earth's, which has a solid inner core wrapped inside a liquid outer one, a difference that helps explain why Mars lost its global magnetic field billions of years ago, while Earth's has endured. Now the scale changes entirely, because next is Jupiter, a planet with more mass than every other planet in the solar system combined, roughly 2.5 times more. Land in the middle of what's effectively an ocean, the single largest ocean anywhere in the solar system, made not of water, but of liquid hydrogen. The drill slides easily through the outer surface since there's no rock or solid metal up here, only gas thinning into liquid. But the pressure builds fast, and by the time you're deep inside, it's become genuinely unimaginable, rattling even a drill engineered to withstand it. Reach Jupiter's core, and the temperature there sits around 90,000 degrees Fahrenheit, hotter than the surface of many stars. And the core itself isn't a solid ball at all, it's liquid, held together only by the sheer, crushing weight of everything pressing down from above. Time to get out before the drill gives up. Even from orbit, Jupiter's real danger isn't just heat and pressure, it's radiation. Since the planet's enormous magnetic field, the strongest of any planet in the solar system by a wide margin over even Saturn's, traps charged particles into radiation belts so intense they would fry unshielded electronics within hours. A hazard engineers had to design around for years before Juno ever launched, wrapping its most sensitive electronics inside a specially built titanium vault just to survive the trip. From there, drop onto Europa, one of Jupiter's most closely watched moons, a vast icy wasteland streaked with reddish cracks and ridges. Drill through the ice, which is only 10 to 15 miles thick, and beneath it sits an enormous saltwater ocean, more than twice the combined volume of every ocean on Earth. The deepest trench on our own planet, the Challenger Deep, drops just over 6 miles down. Europa's hidden ocean may go as deep as 100 miles. NASA's Europa Clipper mission, launched in October 2024, is currently on its way there specifically to study whether that buried ocean could support life, and it's expected to begin its detailed flybys in 2030 once it arrives, using ice-penetrating radar and a magnetometer to search for direct evidence of that hidden ocean without ever having to land or drill through the ice itself. Push through the water to the ocean floor and you'll hit a rocky mantle, much like Earth's, and not far beneath that, Europa's small metal core, reached fairly quickly since the whole moon is smaller than our own. Skip over to Io, another Jupiter moon, and the single most volcanically active body anywhere in the solar system. A volcano twice the height of Everest is erupting on the surface as you drop beneath it, and even underground nothing here sits still. The interior is molten, streaked yellow and brown from enormous quantities of sulfur, and the whole moon is being physically kneaded by Jupiter's gravity and the pull of its neighboring moons, a process called tidal heating that makes Io's entire surface swell and sink by more than 300 feet, over and over like the world's slowest, largest tsunami, except made of rock instead of water. Keep pushing down and it finally calms, ending at a hot but stable iron core. Then Saturn, the second largest planet in the solar system and easily the most photogenic thanks to its rings. The drill simply falls for a long stretch through gaseous hydrogen and helium, nothing to cut through, just pressure steadily building until that gas turns to liquid hydrogen. Continue down and you reach a solid core made of iron and nickel, surprisingly compact given the planet wrapped around it. And finally, Neptune, out at the edge of the solar system, where the drill has to anchor itself immediately against winds that blow roughly 5 times stronger than the most destructive hurricanes ever recorded on Earth. Beneath a thin outer layer of hydrogen and helium sits a bubbling, superheated slush of water, methane, and ammonia. Hot, despite Neptune's reputation as an ice giant, a name that actually refers to the core buried far below. A small, ancient ball of rock and ice that stays freezing cold no matter how violently things are churning above it. Now let's zoom back in on that great red spot, because Juno's 2017 flyby was only the beginning of the story. Jupiter's temperatures in the upper cloud layers sit around minus 234 degrees Fahrenheit, and the great red spot itself runs colder than the surrounding atmosphere. But directly above the storm, in a patch of upper atmosphere that shouldn't be unusually warm at all, instruments recorded temperatures spiking to roughly 2,400 degrees Fahrenheit, hotter than lava here on Earth. Some astronomers believe turbulence from the storm itself generates gravity waves and sound waves that dump enormous amounts of extra heat into that one specific patch of sky, though the mechanism is still debated by planetary scientists who continue analyzing data from Juno's extended mission, which has now flown past the Great Red Spot multiple times since that first historic pass. People have tracked the storm for more than 150 years, and for a long time, astronomers assumed it was slowly shrinking toward extinction. Then, after analyzing decades of Hubble Space Telescope images, researchers found something nobody expected. The winds at the storm's outer edge were actually speeding up, gaining roughly 1.5 miles per hour of extra speed every single Earth year. It's a small shift, but it flipped the entire assumption about the storm's fate. At its outer boundary, wind speeds can reach 400 miles per hour, faster than any tornado on Earth, while the center of the storm barely moves at all. Nobody knows for certain what feeds it. Jupiter has no solid ground to create friction that would slow a storm down, and scientists suspect the Great Red Spot may have formed when several smaller storms merged together long ago, and that it keeps itself alive today by continuously swallowing smaller vortices and drawing hot gas up from below and cool gas down from above. Some researchers have gone so far as to suggest that if the Great Red Spot ever does run out of smaller storms to absorb, it could eventually begin to genuinely shrink for the first time in recorded history. A slow-motion process that would still likely take many decades to become obvious, even to astronomers watching closely. As for that deep red color, One leading theory suggests a colorless layer of gas near the storm's upper boundary reacts with ultraviolet radiation from the sun, essentially getting sunburned into the reddish hue we see from Earth, though that too remains an educated guess rather than a confirmed answer. Jupiter isn't the only planet hiding a monster storm. Saturn has one too, called the Great White Spot, a storm that erupts roughly once every 30 years and eventually stretches a tail of clouds all the way around the entire planet. At its peak, it functions less like a single storm and more like a colossal system of interlinked thunderstorms, generating lightning that can flash more than 10 times every second. Nobody is entirely sure what powers it either, with some researchers pointing to solar heating and others arguing the storm's cloud structure only makes sense if Saturn has some internal heat source driving it from below. Head out even farther, and Pluto, the largest known dwarf planet, has its own quiet mystery, an atmosphere that rises unexpectedly high above the surface and is layered more than 20 times over, each layer bitterly cold and thin. Even our own moon technically has something similar, an extremely faint exosphere made of helium, neon, and argon, roughly 10 trillion times thinner than Earth's atmosphere, so sparse it barely counts as air at all. NASA's New Horizons spacecraft, which flew past Pluto in July 2015 after a 9-year journey across the solar system, confirmed that this thin nitrogen and methane atmosphere actually extends more than 1,000 miles above the dwarf planet's surface, forming a faint blue haze that surprised scientists who had expected something far more modest, given Pluto's tiny size and frigid distance from the Sun. And if you're traveling through deep space on this journey, it's worth watching out for black holes, regions where gravity is so extreme that not even light can escape. Every so often, a black hole flares violently, blasting out enormous amounts of energy and carving gaps into the surrounding gas and dust. In February 2020, astronomers using radio and X-ray telescopes confirmed one of the largest explosions ever recorded in the universe, an eruption from a supermassive black hole at the center of the Ophiuchus galaxy cluster, roughly 390 million light-years from Earth. The blast was so powerful, it carved out a cavity in the surrounding hot gas large enough to swallow roughly 15 Milky Way galaxies side by side, and researchers estimate the eruption released about 5 times more energy than the previous record holder. To put the scale of that blast in perspective, the astronomers involved compared it to a volcanic eruption capable of carving a crater the size of the Grand Canyon out of solid rock, except playing out across intergalactic gas on a scale that dwarfs anything a single galaxy, let alone a single planet, could ever produce. One more stop before we head home, because if you land in the wrong place, you could end up somewhere like K2 141b, an exoplanet first spotted by the Kepler telescope in 2017 and confirmed in 2018, sitting about 200 light years away. At first glance, it resembles Earth, with oceans that evaporate, form clouds, and rain back down. Except on K2 by 141b, it doesn't rain water, it rains rock. The planet orbits its star so tightly that a full year there lasts just under 7 hours, leaving one side permanently locked in blistering daylight with surface temperatures above 3,000 degrees Celsius, hot enough to vaporize solid rock directly into the atmosphere. Supersonic winds, reaching speeds well over 3,000 miles per hour according to the 2020 study that modeled the planet's atmosphere, carry that rock vapor across to the permanent night side, where temperatures plunge to nearly minus 200 degrees Celsius, cold enough for the vapor to condense and fall back down as rock rain and rock snow, sliding slowly back toward the magma oceans below. Not exactly a vacation destination. Researchers studying K2, Hoover 141b, believe it may actually represent an early, violent stage that every rocky planet, Earth included, likely passed through billions of years ago, before cooling and solidifying into the calmer world we know today, meaning this hellscape might be less an alien curiosity and more a distant mirror of our own planet's forgotten childhood, back before oceans, before continents, before anything resembling the world we now call home. Now, let's bring this back to Earth with the strangest hypothetical of all. What would actually happen if our own planet somehow became the size of Jupiter? There's almost nothing in common between the two worlds as they stand. Earth is a small, temperate rock covered in oceans and forests. Jupiter is a gas giant so violent that anything falling into it would likely be torn apart before ever reaching a surface, because there isn't one. But imagine stretching Earth's radius out by roughly 11 times, matching Jupiter's actual size. If the density stayed the same, the resulting planet's mass would balloon to nearly 4 times greater than Jupiter's real mass, an object so large it's hard to even picture. The very first thing you'd feel wouldn't be the sheer size of everything around you, it would be gravity, roughly 11 times stronger than what your body is used to. Researchers generally agree the human body could plausibly adapt to gravity up to about 5 times Earth's normal pull, but beyond that, the math stops being forgiving. Doctors and physiologists who study the effects of long-term bed rest and hypergravity training on the human body generally agree that anything much beyond that threshold would place unsustainable strain on the heart, lungs, and skeletal structure, essentially trapping anyone who tried to live there in a permanent crushing weight they could never fully adapt to. Assume we tried it anyway. Every single step would leave you needing to sit down and recover like you just finished a marathon, and standing back up would be its own grueling task. Getting through daily life would require serious muscle mass just to reach the refrigerator, ironically solving the junk food problem by making the act of retrieving junk food a full workout. Gravity that intense doesn't just make movement harder, it reshapes the size of everything. Astronauts actually gain a small amount of height in microgravity because their spines stretch out without gravity compressing them. So it stands to reason that the opposite, extreme gravity, would compress and shorten everything on the planet's surface. Trees would struggle to grow tall at all, since pulling water up from root to branch against 11 times the gravity would be close to impossible, likely shrinking most plant life down into squat, ground-hugging shrubs. Mountains would flatten out under the added weight pressing down on the crust, meaning Everest's summit would suddenly become a far more achievable climb. Ironic, given how much harder simply walking there would be. Animals would be forced into a similarly compressed shape, and anything that depends on flight, birds especially, would likely lose that ability entirely, since generating enough lift against 11 times the gravity would demand wings and muscles far beyond anything evolution could plausibly produce in time. Breathing itself would become a battle. Atmospheric pressure would climb dramatically because a planet with dramatically more mass pulls its air down with dramatically more force, effectively compressing the entire atmosphere into a denser, heavier blanket pressing down on everything below it. That same pressure shift would also disrupt ordinary water chemistry, making it harder for water to boil and easier for it to remain locked as ice or vapor depending on conditions, and much of the planet's ice would likely melt outright, while cloud formation collapsed into sudden overwhelming downpours rather than the steady rain cycle we're used to. Flooding on a global scale would become a real and immediate risk. Not everything about a Jupiter-sized Earth would be pure catastrophe, at least at first glance. With the radius stretched out so dramatically, the total surface area would multiply many times over, opening up enormous stretches of newly available land, at least in theory. But that openness would be mostly meaningless in practice because crossing oceans that are now roughly 10 times larger and deeper than they are today would become nearly impossible, and flight, along with any hope of future spaceflight, would likely be off the table entirely given the added atmospheric density and gravitational pull working against any aircraft or rocket. Then there's the geology, and this is where things turn genuinely apocalyptic. A planet with nearly 4 times Jupiter's mass packed into Earth's original material would become catastrophically unstable internally. Every dormant and extinct volcano on the planet would likely reactivate at once, flooding the surface with lava and toxic gas. For a sense of scale, consider the 1883 eruption of Krakatoa, still recognized as one of the most destructive volcanic events in recorded history, an eruption so powerful it destroyed the island itself, triggered tsunamis felt across entire ocean basins, and darkened skies with ash for months afterward. Now, imagine that kind of event occurring simultaneously at volcanic sites across the entire globe. Closer in overall devastation to the Chicxulub impact, the asteroid strike roughly 66 million years ago that ended the age of dinosaurs by kicking enormous volumes of ash and debris into the atmosphere and choking off sunlight for years. Worse still, that internal instability would likely destroy Earth's magnetic field entirely. According to planetary scientist Rory Barnes at the University of Washington, that magnetic field is what currently shields the surface from harmful cosmic radiation and solar wind. It's generated by the slow churn of molten iron deep in Earth's outer core, and if the added gravitational pressure from a Jupiter-sized mass forced that molten iron to solidify, the magnetic field would collapse, leaving the surface directly exposed to radiation streaming in from space. There would be a strange silver lining hiding in all this destruction, though. Jupiter's real gravity currently acts as a kind of cosmic shield for the inner solar system, sweeping up an estimated 24,000 impacts a year that might otherwise threaten smaller planets like Earth. A Jupiter-sized Earth would inherit that same job, catching debris that currently sails past harmlessly. Meanwhile, the Chicxulub-level asteroid strikes that occur roughly once every 100 million years under normal circumstances would become vastly more frequent, potentially rolling in on an alarmingly regular basis instead of once in the entire history of complex life. The moon wouldn't survive the transition either. Sitting as close as it currently does, our growing planet's intensified gravity would likely tear the moon apart entirely, its fragments either raining down onto the new surface or scattering into a debris ring, echoing the leading scientific theory that the moon itself formed billions of years ago from debris after a Mars-sized object struck the early Earth. If the moon somehow survived intact, the resulting tidal chaos alone would trigger enormous, unpredictable waves across every ocean on the planet. Over time, the planet might even accumulate brand new moons of its own, since real Jupiter currently has 79 confirmed satellites, though thick volcanic haze from all those simultaneous eruptions would likely block any clear view of them from below. Astronomers who study moon formation around large planets note that most of Jupiter's smaller moons were likely captured asteroids rather than objects that formed alongside the planet, meaning a Jupiter-sized Earth might slowly gather its own chaotic entourage of captured rocks over millions of years, rather than gaining a full moon system overnight. The ripple effects wouldn't stop at Earth's new front door either. A second gas giant-sized planet suddenly appearing in the inner solar system would nudge the orbits of every other planet nearby and subtly shift Earth's own rotation. Because of the planet's now enormous mass, a full orbit around the Sun would take dramatically longer to complete, mirroring how 1 year on the real Jupiter is equivalent to roughly 12 Earth years, a shift that would completely upend the length and rhythm of the seasons as we know them. Every calendar, every planting season, every migratory pattern that any surviving life had ever depended on would need to be rebuilt entirely from scratch around a year 12 times longer than the one every living thing on the planet had evolved around. Between the collapsed magnetic field, the reactivated volcanoes, the crushing gravity, and the chaotic new orbital dynamics, the honest answer to whether life could survive on a Jupiter-sized Earth is almost certainly no, not in any form remotely resembling life today. But if astronomers ever do find a genuine Jupiter-sized world sitting at just the right distance from its star, with the right chemistry and the right conditions, it would still be one of the most fascinating places in the galaxy to study, even from a very, very safe distance. And maybe that's the real takeaway from drilling through an entire solar system's worth of planets and moons, that the line between a livable world and a genuinely hostile one is often frighteningly thin, sometimes nothing more than the right size, the right distance from a star, and a core that happens to still be turning.